Yep, welcome to today's MEE Live. I'm going to hand over to Rich. Hopefully, you can share your slides.
Okay.
And yeah, so if you've got any questions for Rich, do feel free to type them into the chat as he's going, and I can ask them all at the end. Or at the end, you can unmute yourself and ask a question if you prefer to do that. So whichever you like. But do start typing the questions as you think of them. I'll ask them all at the end because sometimes otherwise we're sitting here just waiting for people to finish typing. Anyway, well, over to Rich to talk to us about ADAPT3.
All right. So thanks very much. And thanks very much for coming. So my name is Rich Shefferson. I'm doing this from Japan right now. So maybe you guys are waking up, but this is not coffee anymore, but enjoy your coffee. Um, and so today I'm going to talk to you about ADAPT3, which so the MEE paper on this is just out on early view right now, I think. And So ADAPT3 is an R package, and it's meant to handle matrix-based approaches to two different things, adaptive dynamics and community projection. And so when I say matrix-based approaches here, I'm referring specifically to using matrix population models within the context both of the evolutionary ecology side, which would be adaptive dynamics, and community ecology side, which would be community projection. In terms of adaptive dynamics, so I'm referring essentially to that a mathematical simulation-based approach to study microevolution and speciation. Most commonly, it's used to test hypotheses of trait evolution, and in particular to look for things like optimal trait values, like evolutionary stable strategies, or to predict how natural selection might act in a population. Um, it's used often in game theoretical contexts because basically in a typical adaptive dynamics simulation, frequency dependence and density dependence both operate. And so you can actually do tests of classic games or more interesting newer games. The two sorts of approaches that the package handles, these are generally the two approaches to adaptive dynamics, but both are handled by ADAPT3. So pairwise invasibility analysis and multiple invasibility analysis. In the pairwise case, basically we're looking at trying to test the competitive ability of a range of trait variants against one another in pairs, whereas in multiple invasibility analysis, we might actually dump all sorts of different trait variants together to see the result of that competition. Um, in terms of pairwise invasibility analysis, the procedure generally starts with the definition of all the possible trait variants. I think a lot of people like to use quantitative traits in this case. So you might think about a spectrum that a trait can take a value on, and then you might pick a systematic number of points along there that you will test. And sometimes the traits that are tested are a little odd. In my case, I'm a demographer and using matrix-based approaches. What that might mean is that I might have sort of regression equations that I'm using to propagate vital rate values. And so in this case, I might have because I work with plants very much, I might have a probability of flowering. The probability of flowering is determined via a regression model. In that regression model, that might be like a logistic regression, and there might be a y-intercept to that. So I might, for example, test the tendency to flower by coming up with a range of additive deviations to that y-intercept. So if I make it more negative, then there's less flowering. If I make it more positive, then there's more flowering. And so then the trait spectrum that I'm working with is additive deviations to the y-intercept in that case. And in the pairwise invasibility case, then all possible pairwise permutations of those trait values are developed and explored in a simulation context. Typically, what will happen is that in each pairwise case, one of the trait variants is going to be considered what's known as the resident. And so what happens there is that we start the population with maybe a single individual or a small number of these individuals. And we allow the population to grow to some maybe carrying capacity or some plateau, depending on what kind of density dependence you're using. It might not be a plateau, but it might be some kind of oscillation or something like that. And after the population has been at that plateau level for a long enough period of time, we introduce a single uh, mutant trait variant that now has to compete against the rest of the population. So that would be referred to as the invader. And really, what's interesting here is how the invader does. What happens shortly after its introduction? That's referred to as invasion fitness. And the result of that is typically a pairwise invasion plot or a pairwise invasibility plot. I have to warn you that the colors sometimes mean the exact opposite of what you see here, but basically these plots are showing you areas where the invasion fitness is either positive, so that means that the invader is actually invading into the population, and areas where it's negative, so those would be areas where the invader can't compete against the resident. And you see there's a resident strategy and invader strategy on the X and Y axis. So when along the diagonal of a slope of one, you have basically trait variants competing against themselves. And so right there, the invader is the resident. So you have no difference. So what's interesting in these cases is, of course, not this scenario. This scenario suggests that as you increase whatever trait value you have, you're going to have just increasing values selected for. What's interesting is more like this scenario here or this scenario here. These suggest optimal trait values. In this case, this would be an ESS value here. So basically, if you have a low value of the trait, then it evolves. Natural selection will keep selecting for higher values up until some point. If you start off with a very high level of that trait, then natural selection will select for something lower towards that point. Um, this is from another paper about 13 years ago, a very good paper called The Hitchhiker's Guide to Adaptive Dynamics, which I highly recommend, showing you a few other sorts of scenarios that you can come across. There are many more. These show you different kinds of trait optima, but they're not necessarily stable. They're not necessarily ESS in the kind of Nash sense. So you might have different sorts of dynamics resulting in these various cases. Um, in multiple invasibility analysis, there's generally no set figure for this. This is a good deal more complicated and harder to interpret. Um, in a nutshell, you start off with maybe some resident that you're incorporating, but you start incorporating new genotypes either shortly after introducing the resident or you wait until there's a plateau. And then you could put in several, or you could put in generation by generation as you go. And then the question is what happens to trait evolution in this context? For me personally, adaptive dynamics originally was about trait evolution, but my interests right now are in adaptive speciation. And for those of you who aren't familiar with this body of literature, I would encourage you to look at it. It's really fascinating. The idea here is that sympatric speciation could result from frequency-dependent selection. And adaptive dynamics happens to be a perfect approach to investigate whether it can happen. And so there are a number of interesting papers that have been released over the last 25 to 30 years exploring this. Some of them using a matrix-based approach, which we're using here, that assumes clonality. Others assuming a more sex-based and individual-based approach. Um, Now, ADAPT3 also does one other thing, which is community projection. And this might seem an odd mix, given that I was just talking about adaptive dynamics. But it turns out that methodologically, a matrix community model, the community projection, if you're doing it a matrix-based way, it turns out to be methodologically very similar to adaptive dynamics, at least in terms of what goes on in the background. A matrix community model, basically what happens there is that imagine you have a community and you've been monitoring several species in it demographically over a number of years. So you can set up a matrix population model for each of those species. And then instead of just assuming that they're all independent, you could create a common density dependence framework, say choose some vital rates across the different matrix population models that you have that's going to be basically assumed to be influenced by competition with the other species, whether it's direct or indirect competition. And so in the adaptive dynamic side, we also have, of course, density dependence that forces competition. We're just assuming multiple genotypes within a species. In this case, it's the same thing, except we're assuming multiple species within a community. And we're not doing pairwise invasibility plots or anything like that. We're just seeing what happens down the line with the communities. Um, this is a figure from a paper released 3 years ago by Dave Little. And I would kind of recommend, if you're interested in matrix community models, to have a look at this. It sort of is the grand result of a lot of work that Dave Little himself has done over the last 20 years, developing some of the theory for this and developing some of the empirical work. And it gives you an idea of how matrix community models operate. One of the reasons that people are interested in this approach is because it sort of assumes a sort of a reductionist approach to communities that allows you to test maybe certain kinds of null models or other sorts of models for how communities might behave across time. So you could actually develop these matrix community models, project them forward, and then try to assess both their impact on basic community metrics or you can assess how, say, one population reacts to changes in another population within the same community. And so in Dave's work, he introduced, for example, sensitivity and elasticity analyses within the MCM framework, where you could ask how a community metric or a population growth rate of some other species or abundance or whatever you're interested in is influenced by different vital rates across the matrix community model. So, how do we run ADAPT3? So this is an R package. I would recommend not simply R, but R Studio, and I would recommend that you have the newest versions. So ADAPT3 is actually mostly written in C++, and so it depends on the RCPP packages that are written by some of the members of CRAN. And so if you have the newest versions of R, it'll work smoothly. If you don't, at least I think have something, I guess the earliest would be maybe 4.5 at this point. ADAPT3 depends on package LEFCO3, which sort of develops the grand working environment for matrix population models that's used here. So you have to install both. They are both on CRAN. CRAN has the stable versions. There are development versions, though, that I run, and the little line of code that you see here is something that'll install whatever the current development versions are. LEFCO3 right now, the stable version on CRAN is the top version. But for ADAPT3, there is actually a higher development version right now. I'm not going to release the stable one for probably another month or so. Okay, so what's the procedure? Once you have everything installed, the first so this, by the way, is a figure in the paper introducing ADAPT3. Start off by developing our NPMs. Then if we're doing adaptive dynamics, we develop what's known as a trait axis. Then we go into weighting individuals, setting start vectors and times. And I'll explain all these in just a moment, but just to give you a basic rundown. One of the most important things we have to do here is set density dependence. If we don't do that, we're assuming everything is running independently. Package NPMs into lists. This is for the matrix community model case only. Then we run our simulations and try to analyze the results, and there are some functions within ADAPT3 that can help with that. Okay, so just to start off with NPM creation, so ADAPT3 relies on LEFCO3. You don't have to create matrices in LEFCO3 in order to run ADAPT3, but you have to at least import whatever you've got. LEFCO3, so for those of you who have interacted, for example, with the Compadre and Commandre databases, so there are functions within LEFCO3 that will allow you to import directly from those databases, whether you are online and doing it that way or whether you've downloaded your own version, both work. And the import procedure is rather important because there are essentially, there are aspects to the import structure or to the NPM structure that we develop in R that gives a lot of metadata for understanding the NPMs themselves. It could be used both, in your case for inference as well as by R itself in order to make the right calculations. Now, the next step, this is only if you're doing adaptive dynamics here, would be to develop a trait axis. So a trait axis here, this is with the trait axis function. Basically, what you're doing here is you're identifying what these different trait variants are. So there are a lot of different trait variants that you could work with. If you're working with vital rate models that are populating your matrices, then you can put deviations onto their y-intercepts. That's all taken care of within here. Or if you're just importing like empirical NPMs directly, then you can actually create trait variants that alter specific elements within those matrices by some amount. You know, so for example, if you have like 10 trait variants, and all of them are altering fecundity, and maybe there's one fecundity element, then you could put all sorts of deviations on it or multipliers on it. Or if fecundity is like a Poisson regression model or something, then you can work with the y-intercept. Um, Now, for both the adaptive dynamics case and the community modeling case, the next step would be to weight individuals. If you don't do this step, then R will assume every individual counts as one, and that each individual of each stage, of each species, of each genotype will count as one individual. And you might not want that. In the examples that I'll show you today, particularly in the MCM case, so the authors decided to basically consider every individual as being some multiple of a cottonwood seedling. So, because you might imagine adults are like several 10,000s or more seedlings. In some other species, their seedlings are worth less than a cottonwood seedling. And this is all in terms of the common aggregate density. There are also situations with plants in particular where you might want to zero out a stage in terms of its effect on the aggregate density. So, for example, if you're working with plants that have dust seeds, those dust seeds should probably be set at zero because they're not really doing anything in the population. You might have vastly more of those than of actual growing individuals. And so that could impact your density dependence functions in a not so great way. So that's something to think about and to set. The next step would be to set the start vectors and times. A start vector would be what numbers of individuals should each population or each genetic variant start with. And so you, by default, there will be one individual per stage uh, of each case. And you probably don't want that. If you're running adaptive dynamics, you typically want to start with a single individual. So you'd have to choose which individual, what kind of individual that's going to be, which stage. So you could set that. Or if you're working with actual empirical data, maybe you have a good idea of how many individuals there are of each stage, and you want to make a realistic projection. So you start with those numbers. So you can set that. And then you also have to decide on, how long the projection will run and when each species or each genetic variant is going to be incorporated into the projection. In the adaptive dynamics case, of course, the resident might start at zero, but then anything you introduce later on that's going to compete with it should be later. And so you might have to do some experimentation to decide when that would be. In the community case, maybe you want to start everything at the same time or maybe not. In terms of density dependence, so right now there are five main density dependence approaches that are packaged into ADAPT3. If you have ideas for more, please let me know because I'm very happy to incorporate more. These are all functions that work on specific matrix elements, okay, within the NPMs. And so I think really that the most commonly used ones have a tendency to be the Ricker and the Beaverton-Holt. And probably which one you're using depends on whether you're a theoretician or a fish biologist or what you're doing. The Usher equation is put in, it's a bit more obscure, but human demographers sometimes like that one. And the logistic equation, this is there are two variants of the logistic equation because this is the logistic equation with a minimum of a one time step lag, so it can incorporate an oscillation. There is a fifth density dependent equation here, which I refer to as the additive limit equation. This is based on what's known as the recruitment box model. This comes from Dave Little's work, and in particular his incorporation of some previous work. I don't remember the original paper that developed the recruitment box, but the idea there is to have an instantaneous response to some resource that's being taken up by whatever individuals are there. And so then basically this, if this is a community, the species are essentially take up that resource in order until it's full. So this will be used in one of the examples that I show later. In the case of the matrix community modeling, the next step would be to package all of the NPMs together in a single list. You don't have to do this for adaptive dynamics because there's only one NPM that you're generally using for the adaptive dynamics case. And then finally, we get to running the analyses and interpreting the results. In the adaptive dynamics case, the main function is called invade3, and that function will actually create the basic data frames that can then be plotted as pairwise invasibility plots. There will also be a data frame in there, provided that you set the argument to true, that will give you an invasion elasticity analysis to give you an exact, well, an estimated value for any trait optima that occur. And there are some plotting functions that can allow you to look at genotype trends, for example, to look for evolutionary branching. In short, it gives you a ton of data. On the community projection side, there are functions that will run sensitivity well, there are functions right now that will run the sensitivity analysis, not yet elasticity, but you can do that on your own. And you can, of course, also create community metrics with the data that you get. The actual output structures, so they're list structures with 7 or 8 core elements. And there are 3 core elements in each case. If you're running a matrix community model, then the core 3 are these: ag density, and out, and structure. Ag density is basically a matrix, and what it does is it shows you the aggregate community density by time and replicate. So the aggregate community density is not the sum of the number of individuals, but the sum of the individuals multiplied by their stage weights in each case. N out will give you a list of matrices giving the species numbers per time by replicate. Okay, so ag density will give you by replicate within a single matrix. This will sort it out a bit more. And then structure is a 2-level list that gives you the number of individuals per stage, per species, per time, per replicate. So really just base level, all the results dumped out for you. So you can do with it what you want. And then a bunch of metadata. For adaptive dynamics, running invade3, so the 3 core elements, so they're sort of parallel with the community ones. Fitness is a data frame that shows you the resident and invasion fitness per run. N out is very similar to N out over here. It's a list of matrices giving genotype numbers per time by replicate. So each list element is a replicate. And then variance out is a 2-level list giving individuals per stage, per genotype, per time, per replicate. So like structure. If you run the elasticity analysis as a part of this, it'll have a 4th element that will give you a data frame giving you the elasticity results to show you where the trait optima are. Okay, so that brings me to the 2 case studies. There are 2 case studies that are packaged within the paper. And so I would encourage you to pick up the paper. There's both R code in the form of our notebooks as well as PDFs showing what the output looks like, because there are some steps that might take a while, so you can take a look at what you're supposed to get. The first case study is from a paper that I published 12 years ago in the Journal of Ecology. And it's not the entire analysis, but just one part of it. Basically, that paper was focused on the concept of vegetative dormancy in herbaceous perennial plants, and this is just something that occurs in some plants where You would think that because they're photosynthetic and they flower, that they should be sprouting every year, but it turns out that they can live underground without any sprouts, no photosynthesis, no reproduction for sometimes many years at a stretch. And I've been studying this phenomenon for, well, a quarter century, basically. And so one of the key questions that I've had over the course of that research is whether this kind of dormancy is adaptive. If so, how? Um, the main reason that it's a question is because whenever you look at the demography of dormancy, you find that it doesn't look that great. Dormant individuals, if an adult, is flowering one year and becomes dormant the next, the associated survival probability, annual survival probability of that individual drops. And so when I started working on this phenomenon, the thinking was that maybe it wasn't adaptive. Maybe it's a maladaptive condition, and there's something just keeping it within the life history, preventing selection from taking it out. So for this case, well, for this particular paper, I worked with two study organisms, Cypripedium parviflorum here, and then Anemone americana in two different parts of the U.S. The Cypripedium case, I think I had, I don't remember, over 10 years of data, if I remember right. And in the anemone case, it was 5 or 6 years of data. And so they're life histories, fairly complicated life histories, as you can see. Um, and worked out some of the basic demography. And what I suspected in this case is that it might be that vegetative dormancy winds up being adaptive if we consider a long-term individual history. So it could be, for example, that if you are typically a very small individual and you're not eking it out very well in the environment anyway, then dormancy might on some occasion actually boost your survival. And if you stay, for example, if you're a small individual and you become big in the next year, using up all your resources to create that big above ground structure, then it might be that your survival, in order to maintain it, you would have to go dormant the next year because of a cost of growth that you're going to pay. Those sorts of costs are usually not, they're not costs that you can actually find in a matrix model because a matrix model basically dissects the demography down to pairs of times, like consecutive times. And a cost of growth would be something that you would see over at least 3 times, right? So I developed historical models. So these are matrix models that have 3 time steps in them. And as well as more normal matrix population models that have the 2 time steps. I basically tested for what might be the right kind of density dependence here. I ended up using a Ricker function on germination simply because it looks like germination is very commonly negatively density dependent in plants, and other authors have assumed the same scenario. And so I basically worked out a scenario where I could basically create a plateau using using density dependent germination, where basically germination was multiplied by a Ricker function. And in the case, so I developed these 2-year models, the standard MPMs, as well as the 3-year models, the historical models, and then deterministic and stochastic versions. I don't think I show. I don't remember if I did a stochastic version of the historical actually, but in any case, I did a stochastic version of the normal one, thinking that it might be that this is vegetative dormancy might be a bed hedging trait. So in that scenario, you might see it in a stochastic projection. In the case of anemone americana, so this is showing you the results. This is a deterministic 3-year plot. And so this is showing that we have an ESS additive deviation to the y-intercept for sprouting, which is what I was working with here, suggesting that here maybe this cost of growth actually works. But the key example I wanted to work with that I incorporated into the paper is this one for Cypripedium parviflorum. And here I found that all of the models worked, and the simplest model is a deterministic 2-year model, so the standard small matrix population model. And that suggests that vegetative dormancy is just strictly adaptive. And so we have in that paper an additive deviation to the y-intercept that's a little negative in this case. So For this, I basically recreated this analysis. However, I updated the data, and now I rewrote the methodology essentially in basically simplifying a lot of the earlier stuff with Lefko 3 and then tossing it into ADAPT3. I still see an ESS. It's a different additive deviation, but honestly, the sprouting probability model is a different model in this case because the data is a little different. Um, so all the data that was in here was incorporated, but they've got a bit expanded. Okay. So we still see the same, we still see an ESS here. We still see that there's an intermediate value of sprouting, so vegetative dormancy is adaptive at some levels. Okay, so there's an example that'll work you through how to do this and how to get this plot. The second example is of a matrix community model. And so I have to acknowledge that this is based on someone else's work. This is Dave Little's work. I really highly recommend you read his work on matrix community modeling to give you an idea of how to develop your own further and to give me, feedback because I would like to put more kind of power into this. So the particular paper that I wanted to rewrite in ADAPT3, essentially the analysis that I wanted to rewrite in ADAPT3 is from Ecological Applications 2017, this linking river flow regimes to riparian plant guilds paper. And what happened in that paper? So so Dave was interested in exploring these arid communities in the Great Basin in the U.S. and in testing to see how the plant communities are going to respond to potential changes in climate, whether that means getting drier or getting hotter. I focused the analysis that I was redoing on the getting drier versus wetter um, analyses that he was doing. He developed some five matrix population models for this. They're not pure populations, though. They're more like species guilds. Um, One of them is a hydro-riparian tree, which is actually that actually is, I believe, a true MPM because it's a cottonwood species, Populus fremontii. But I think the other four, for the most part, species guilds, like the zero-riparian shrub. Here I put an example of a tamarack species, but there's a few tamarack species that could be included. The mesoriparian meadow would be primarily grasses, but not all. Hydro-riparian shrub this would be a willow species, typically Salix exigua, but I don't think it's exclusively that. And desert shrubs. And so their goals were to develop MCMs to test how this riparian plant community in the sorry for my spelling there, in the Great Basin might change as a result of changing climate. And so that's what I wanted to recreate here. They also did a lot with sensitivity and elasticity analyses, and I recreated a little bit of that, but only a little bit. Um, the framework that they use, so this is the same slide as I showed you before. And the nice thing here, I contacted Dave in order to make sure I was kind of understanding his logic and his code. But his code is completely available. If you go to this paper, and the 2017 paper in particular, you can find all of the code, all of the data, and you could actually run his version of it versus my version of it and see what you think. Um, what I really wanted to do is to recreate this particular figure from the 2017 paper. This is showing you what they predict will happen to these five species guilds as the drought frequency changes. Okay. Now, one caveat here is I didn't really like their approach to choosing how drought frequency changed. So basically, they have something like 83 years of matrices, and there's functions that they create to create those matrices on based on some data that they provide. And what they did, instead of running a true stochastic model, trying to pick out, say, the actual drought years and just increase the number, what they did is take the first year on and then impose drought into it, which means that some of the matrix elements in these matrices are not going to be responding in the way that they might if you were picking out pure drought years. So I changed that the kind of the approach to stochasticity to make it more in line with how you expect stochasticity work theoretically. And what I got was this, which is qualitatively very similar. There are some key differences, mostly that the here, for example, the cottonwood is predicted to dominate until more or less until you have 80% drought. And then you see the desert shrubs coming in. I have the same pattern with the desert shrubs, but the cottonwoods are overrun by the meadow under a more purely stochastic framework. You could play around with both approaches and see what you like. Now, they also developed these sensitivity analyses and elasticity analyses. I have not worked out an approach to elasticity analysis yet, but I basically used their approach to sensitivity analysis and programmed that into ADAPT3 so you could try it. I did not reproduce this particular figure, but this is showing you how um, population abundance or species guild abundance varies in response to changes in particular vital rates used in each matrix. So you could play around with this and see what you get. So now there are going to be some updates to ADAPT3 coming up. One thing is that I have not yet developed a pure generation by generation multiple invasibility analysis approach yet. The multiple invasibility approach that I have in here has you basically stipulate how many different genotypes you want to test at any given moment, and then to work in the start times for them. But if you wanted to run that kind of more general case of just a new mutant each time, maybe chosen by random, that hasn't been worked out yet. So that's going to be coming up. I'm also working on developing the community elasticity analysis, which shouldn't be very hard given basically it's just an extra step on the sensitivities. And I've been thinking about how to develop lower level sensitivity and elasticity analysis. This is also for LEFCO 3, so I'll probably all come out at one dump onto CRAN. There are two other things that I'm developing kind of in the longer term. One is an individual-based modeling version of this, so where you're not using matrices, although you can use matrices to develop the probabilities. That's going to take some time, probably another year or so. But the other thing that I'm working on is a technical manual. If any of you have worked with LEFCO 3, you might know that there is a very, very large technical manual online. It's free, called LEFCO 3: A Gentle Introduction, and basically runs through tons and tons of different scenarios that you might be interested in projecting. So I've started to develop a technical manual for ADAPT3, and once I get a bit more feedback on how people are using it, I'll be able to finalize that. I expect probably another year on that one. In terms of resources, so as I mentioned, ADAPT3 is on CRAN. So if you can go to the CRAN page on ADAPT3 and just kind of see the status of it there. This is the most stable version. Now, I do have a GitHub repository for it, so you can take a look at that. If you want to look at the code or anything, it's probably the easiest way. The GitHub repository, however, is linked with the CRAN repository on our universe. And so if you want to pick up the latest development version, of ADAPT3, I would go to our universe because our universe, provided that there are no bugs, will actually create all the executable files so that you could since this is a predominantly C++ based package, if you haven't set up your computer to compile, you would have problems with the GitHub repository. So, but here you'll get the executable version, so you can just download the R package for whatever architecture of computer you've got and install that. And then, in addition to all of that, so my lab web page, revolutionarydemography.com, on the project side, I have information and news about packages. So there's the top of it right now is ADAPT3. So you could get some idea of kind of current versions and what further plans are. And with that, I'd like to thank you for your attention, and I'll happily take some questions.
Awesome. Thanks so much. That was really interesting. And yeah, I'm sure all of us are thinking of lots of different exciting ways that we could use this package. Um,
Oh, I hope so.
yes. So I'm just waiting to see if anybody's got any questions. But I guess my first question is always, what's the kind of computational kind of like how much time does this take to run? Does it require like a lot of cores and things, or does it run fairly
Oh,
quickly?
it's basically made to run on a single core. And I do that so that if you want to mess around with parallelizing it, you can do that. Um, So the really how long it takes, depending on how complex you're being. Usually, what that comes down to is how big are your NPMs. If you're running, standard NPMs, or you're working with like a typical IPM, even several of them, then nothing there will take very long. With the caveat that if you're doing adaptive dynamics like the pairwise invasion plots, the problem with pairwise invasion plots is that you need to get a lot of data for them to have really nice resolution. And the problem with that is that to get really nice resolution, you need more and more and more trait variants. And imagine, for example, that you choose just 10 trait variants. So then there will be 100 simulations run in order to try to get the figure worked out. And 100 simulations isn't so much for a small NPM. That could be done, maybe 2 minutes even, depending on your computer. But you might want like 100 trait variants, in which case you've got 10,000. And if you're working with something big enough that requires enough projection time, then that might tie up your computer a bit. So right now I haven't included any cheats to parallelize that, although that is on the horizon. But at the very least, you can experiment with low resolution versions, and then once you decide this looks good, you could increase the resolution, stick it onto Amazon or whatever you're using, and let it run.
Sweet. Um, Anybody got any questions? So you can type them or unmute yourself. Mike's got a question. Go, Mike.
Hi, Rich. Thanks a lot for that. It was a really, really useful introduction to the package. So yeah, really appreciate that. I started typing it out. I've got kind of two self-contradictory points,
Okay.
which is a reflection of me more than anything you've done here. The first is that I think it'd be really nice to include a sort of theta logistic or theta Ricker type density dependent response in there.
Okay.
It should be relatively easy to implement
Mhm.
that in your list of density dependent functions.
Okay.
The reason I think it's a bit self-contradictory is that it leads into the second point, which is around how to incorporate uncertainty in parameter values here. So if you're using Comadre or Compadre or similar,
Mhm.
any kind of these large databases, there is always some uncertainty in the parameter
Yeah.
estimates of vital rates or matrix elements or something. Whether that's explicitly or acknowledged or not is a different issue, but it's there. So I'm wondering if that can that be incorporated within a I don't know a multivariate sensitivity analysis, or is there other methods of doing that you've been thinking about?
Mhm. So I haven't thought very hard about the uncertainty in, say, the vital rates and how we might work with that, except that within Lefko 3 there are bootstrap approaches that are pretty easy to work with. So if you can think of a bootstrap sort of way of doing that, that might get at it, although that's usually more kind of demographic uncertainty, I suppose, as opposed to with the matrix elements or the vital rates. Um, yeah, that's I think I'm going to have to think more about that one because that's a good point. I'm not really sure off the top of my head of how to do it, except to play around with those initial data sets, maybe through some variant of bootstrapping, and then running that out, seeing what the results are like, maybe in that multivariate framework that you're referring to. Yeah,
Yeah, I think it's
yeah,
for
that
me.
might no, that is a starting point.
Yeah, yeah. I think it's a really it's the kind of next frontier of a lot of these
Hmm.
approaches to make the best use of the data that we've got in all these databases. I
Yeah.
think it'd be really helpful for
Hmm.
a kind of constructive push towards dealing with the uncertainty that's inherent in all of that. Um,
Yeah, yeah,
so hopefully there's opportunities for development there. Yeah, great.
sure.
Thanks a lot, Rich.
Yeah, thank you.
Cool. Does anyone else have any questions? Just feel free to just unmute yourself and ask. Everyone's just blown by the possibilities. Yeah.
Well, I would definitely encourage people to just try it out and to give feedback. You could put a GitHub issue or something if you find something isn't working the way you want it to, or you want some extra power. If there's a bug, I've been programming R packages for so long now that I'm just waiting for the bug reports to come in. So
Excellent. Cool. Well, if nobody else has any questions, I think this is a good time to wind up. So thanks again, Rich. That was awesome. It was really cool to hear
you.
about how that works. And yeah, it's always quite different hearing it out loud as opposed to reading it in the paper. So that's a great.
Sure,
And
sure.
yeah,
Yeah,
thanks
thank you.
everybody for coming along. And like I said, if you have a paper and you want to run an ME live on it, please do just get in touch and we'd love to hear from you. So bye everyone. Have a good evening to Rich and a good rest of your day for people who it's the morning.
Bye. Thank you.